Okay, so we've got some code that looks similar to what we had on one of the slides, I think, last lecture. And what we're doing is we've got a function that says add using reference. It takes a reference to a reference that it names A, and then an integer amount. And from our main, we start our balance with 100. Then we make a reference to balance that we call my balance. So what's the first output here for balance?
100.
Okay. Break out the special effects for this. All right, and then we go ahead and we call add using a reference, and we give it balance and 20. So then balance is excellent. Okay, and then what will my balance be?
100.
Oh, some disagreement. So it will be 120. So you can't change it. But so we can see that it's just because my balance is a reference to balance. So if we change balance, my balance changes as well. They're just pointing at the same thing. So if you will do this for me, if you will add a point, if you put your name on it, which I recommend so that I can put it into the Canvas grading thing, and then a point for every correct answer, so up to 4 points on this. And if you will add that up and put it in the score box and then just kind of pass those all in, I will pick them up. And what I will do is I will scan them and they will appear on your Canvas thing, and you should be able to see your full answers and everything. Oh, thank you. All right, was that too bad or feel okay? Don't worry too much about quizzes. Okay, so we'll start with our course logistics as usual. We've still got Programming Challenge 0 going on. Schedule a demo if you haven't. Those are on Friday, it seems like. Has everybody got a demo slot? Anybody having trouble? Okay. All right. So last time you might remember we went through kind of just a tour of C++ concepts. We talked a little bit about references and pointers, some things that you can do. We talked about compile time errors, runtime errors, and then the horrible situation where you don't get either and you just have some logical mess that happens. So today we're going to ultimately start talking about linked list. We'll continue talking about linked list on Friday, and we'll probably even talk about them a little bit on Wednesday. So first, we were writing a class. Last time we met, we were writing a robot class, so I wanted to finish doing that. So I'm just going to jump over here to VS Code. And if you remember, we had written a header file for this robot class that we're making. And we made a constructor, a destructor, and a method called move that just takes an integer x, y. We had some private variables, x and y for the robot. And does anybody know by default what in like C++ a class variable is? Private, public? It's private. I didn't really know that. I mean, I just was working on this and realized that. But in general, you won't have to like know that because you always want to label what you're doing. But if you were to not do that, it would be private by default. So what I want to add to this header is I want to add a name for the robot just so we can, whenever we play with them, we can keep the object straight. So I'm going to include a string so that I can do that. And I'm going to put it as a public field. I'm just going to call it name. It's going to complain at me. Let's see what we got here. try std string. Okay, there we go. So we weren't using the namespace. So we're just adding a field that's the name of the robot. So let's go ahead and jump over to the C++ file where we implement these things. So we implemented our default constructor already. So, and that's just the constructor with no parameters, and we're just setting these values to something we choose. So I'm going to go ahead and change the name to like untitled robot. So we'll have that. And then we had written the move function, and I think we should add probably just a print function, just so we can easily see what's going on with the object. So I'm going to write the method signature for that, and it'll just be a void, and we'll say maybe print status or something. So we've added that to the header file. We'll go back over here to the C++ file and implement that. Print status. And we've got IOStream. So for this, I'm just going to print out the robot's name. So I'll just do robot, and then let's just do name. And we'll say is that, and we'll do whatever position it's at. So, and then we'll do and you can see I didn't do std there. Okay, so now we have the ability to create the robot. We can move it a little bit, and we can print the status. So let's go ahead and just make a new file, and I'll just call it robot test. And I'm going to include IOStream, just because I always do, and we'll use the standard namespace. Okay, then let's write our main function, which will return 0 always, and then we want to include our robots. So to do that, remember we put that one in quotes. Okay. So what we want to do, we'll create an object or a couple of robot objects at this point in the class. But I want to talk to you about compiling this first. So you can see we've got not only, we don't just have one file here. So we've got the robot class that we've written, and we've got our main that we've written. Ideally, in your development environment, when you click on your play button or your debug or whatever, automatically that will take care of passing the right files to the compiler so that it can compile and link them and then execute them. That's not always the case, and so I just want to show you the very easy way to do this. If your editor is giving you problems, because we're only going to write code that has like a couple of files at most, the basic way to do this, so I'm just in a terminal here, and this is just like a terminal on the operating system. This one's just in VS Code. And I'm in this directory that has our files in it. So you can see, let me pull that up just a little bit. So you can see our files are listed there. And I'm going to use G++. You could use whatever compiler you want to use. So I'm going to do the robot test.cpp, because that's our main file. And then I'm going to do robot.cpp, and then I'm going to do an output name just so we have a name for it. I'm just going to call it robot test, and I'll run that. And so then I can do, if I look in my directory again, you'll see that I now have that robot test, and so I can run it. It doesn't do anything right now, but at least we know that our files are all linked correctly. It's compiling with the include statement. So kind of always a good first step, just so that if there is a problem that's related to making sure the files are all getting to the compiler, you find that out first and not with a bunch of other stuff, and then it's kind of harder to differentiate. So, okay, let's go ahead and make a robot. So I'll just make our robot R. And then let's go ahead and give it a name. So since that's a public variable, we can just set it, and just do R2D2. And I'll go ahead and print the status of it to start with, and let's just see that this works. And so, again, I'm just going to run this from the terminal. And so there you can see we've got our, let's see if I can make this bigger. Sorry about that. Ooh, not the whole thing. Okay, can you guys see that at all? I will make a note to make this terminal larger. Actually, let me just... And let's see. Okay, is that better? See that? Okay. Same thing, just the terminal in the terminal app. Okay, so there we go. That's what our output is right now. So we've got the robot's name and 00. That's what we initialized it as. That's what we'd expect. Let's go ahead and move the robot, because why not? 100 and, I don't know, -12 or something. Just make sure that works. So we'll okay, great. So it moves like we thought it would. Now, let's make another robot, but this time, let's do it this way. Name for the robot, anybody? C3PO. C3PO. Okay. All right, so we'll print this one as well. And let's just make sure that works. Okay, so that's working. Does anybody remember the difference here between doing it with this pointer and the new keyword and then doing it just the other way at the top there? So it's a little bit weird, and it's a C++ thing. So the difference in what's going on here is how the memory gets managed, and this will be really important for our data structures.
Isn't it like when you said the pointer points to like the actual value, but if you leave the little asterisk off, it points to the address of it?
Yeah. So this pointer, so this is it's an address to the object itself of the robot. Yeah. In this case, you notice we're using dots versus the little arrow symbol too. So this first way of doing this is actually created and managed by the compiler at compile time. And so the memory that it's using is typically, and there may be some implementation differences, so if you're really into this, don't hold me to it. But in general, it's considered on the stack versus the heap. And that may not have any meaning right now, which is okay. But what you need to know about this first way of doing it is that the compiler takes care of you, and it cleans up after you. And so if you were using this like in a function or something, as soon as that function is finished and its scope is gone, that data goes away because it's trying to clean up after you. That can be a real problem if you don't want the data to go away. And so pretty much everything we do will default to this, because what this does is let us manage that memory ourselves, and the compiler won't do anything for us on that. And we'll talk a lot more about this, so don't worry if that doesn't all make sense. I just kind of want to give you a heads up that yes, there are these two different ways of doing this, And you'll see these, and you'll see this arrow versus the dot. And this is a C++ thing, and we will deal with it as we go through these different data structures. But in general, for us, the most important difference is that one of them, the compiler tries to take care of us, and for what we're doing, we don't want it to take care of us in that way. And the other way, we get to manage a lot more of it. Okay. So I think that's pretty good for just this demo. I will upload a more detailed and commented version of this for you, just for reference, if you want to look at it. But let's get back to...
So would you like writing that in Visual Basics? If we're using a different like program, would the syntax of how we write it be different?
So as long as it's C++, the syntax will be the same. Yeah. And there are some other like syntax ways of doing some of those things instead of using the arrow or the dot. All of them are more complicated, and they make sense like historically, as there was C and then C++ built upon that, and that went on and on. So these are kind of the best, most streamlined ways to do it, the ways that pretty much modern development uses it. But you could see other things.
And I only asked because I seen like when you get the link listing and started typing at the bottom, I've never done that on C++.
Okay.
So like that's possible?
Yeah. Yeah.
Oh, okay.
Yeah. Okay. So let's talk a little bit about memory, and this is going to kind of get us oriented towards linked list. So probably haven't talked a lot about memory in your other courses yet. I think generally like probably operating systems is where a lot of that comes in. How many of you have taken OS? Or is anybody taking it now? Or okay, not yet. Okay, so we're going to do kind of just like the high level view of what we need to know. There's a lot more detail that we can get into, but we'll just kind of work with what we need. So thinking about memory in the computer, which we're just talking about RAM, random access memory, the stuff that's there when it's on, when you turn it off, it's mostly gone. It's where we put all of our data as we're working with things, but we don't expect it to survive long term. So the way that we traditionally think about that, we think about it laid out kind of as a table, if you want. Essentially, we have these slots, and each slot has an address. Now, they might be different sizes, so depending on the hardware, depending on what is happening at levels of software underneath where you're writing. Like in this case, each slot in this case is just a byte. Okay? So a byte, 8 bits of data, and then you see the address 0, 1, 2. We just count up, 1 each time. And there's some examples of what you might find in there. Notation, in case you have forgotten, just like the 0B just means it's binary. So you can expect that what's after the B is just kind of the zeros and ones. And we won't use that a lot, but just so you know what's going on here. So if you look at this table, you can see I'm incrementing by 4 bytes each time. So in this case, I can store things that are a little bit bigger in each of these slots, right? And we're still keeping track of bytes. Bytes is the unit we're going to go to. And we kind of all settled on 8 bits being a byte. At one point, it was 7 sometimes, but that was a very long time ago. So we'll consider 8 bits in a byte, and bytes are kind of the smallest thing that we'll really talk about. We'll talk about the bits occasionally, but bytes are kind of the unit that we want to think about. So in terms of memory, we can think of it as a table with slots for data. Each of these slots has an address, so we can find what's in it. Each slot stores a certain amount of data. The default size of those slots, it might vary, but ultimately, it'll be consistent. So on one system, you won't have like variable length, slots or anything. But one thing to remember about what's in here is that this data doesn't really have any meaning outside of its interpretation of, based on what we're doing. So I'll give you an example. So we're going to zoom in a little bit lower for a second here. So this is just 1 byte. These are all the bits, right? The zeros and ones. Okay. So if we want to say that these 8 bits are going to represent an unsigned integer, so that would mean the biggest number we could represent here is 255, smallest 0. And if you remember, the way we do this is just each place, like this is 2 to the 0, 2 to the 1, 2 to the second, 2 to the third, okay? And if there's a 1 here, we multiply it, we count it, right? So here's kind of the quick math on what we've got here. So this comes down, and we get 65 in decimal base 10, what we work with, when we do math. That's if it's an unsigned 8-bit integer. 65 also means the letter uppercase A for ASCII. So like the ASCII character encoding, which was one of the first things that we had to represent, like letters on the computer. But it doesn't really, it only equals that if that's how we're evaluating it, right? So these bits will look the same in a program that is treating them as an unsigned integer and a program that's going to interpret that as an ASCII character. So to give you a little bit more of an example of this, we've got what we had before, where we've got our unsigned 8-bit integer. And so in this case, we've got a 1 in the most significant bit. We've got a 1 in the least significant. So if we add that all up, do the math, we get 129 in decimal. But what if we wanted it to be a signed integer? So we wanted to be able to have negative numbers in our 8 bits. Well, we can't have 255 anymore, but we can have like 127, in one direction, 127 in the other. So one way to do that that's popular is called 2's complement, signed integer. And here's the little formula to what you do. So you take the most significant bit, so the bit at index 7 here. If it's a 1, we've got a negative number. Then you take the rest of them, and what you do is you flip them, so the opposite of what they were. And then you add 1, ignore any overflow. And then you do that math, you get negative 127 in decimal. So the main takeaway here is that 129 and negative 127 are very different in the terms of what they mean in the end-level software, probably. They're not any different here, though. So one thing that kind of comes with the lower-level data structures is making sure that you interpret it right when you're dealing with like the low-level bytes. So you can think about how this will go further. So this is just 1 byte, right? But obviously, like if you want to have like an integer that can actually count pretty high, or you want to have a double precision point, you may need 64 bits, right? So that's multiple bytes. That's 8 bytes. Now you've got to worry about what order are those bytes in when I send them over the network. Does the other computer do them in the same order that I do them? So these are all things that come up. They won't come up in this class, but they will come up in other classes. But we do want to remember that the data has to have some way of being interpreted. So the same kind of low-level set of bits can mean different things at the higher-level context. So let's talk about arrays for a minute. Everybody used an array or something similar?
We use them, but I don't think I was real good at them.
Okay. So in a lot of like languages, I don't know, like Python or kind of, I guess, the modern languages, they're pretty friendly. You can just kind of add things to an array. You don't really have to worry about it. You don't worry about its size or anything like that. In languages like C++, you might be familiar with like vector, which is a friendlier version of an array that's a little bit easier to use. But let's talk about arrays for a little while here. And what we want to talk about is kind of the limitations of arrays, both like what's good about them and what's bad about them. So an array is and this is important, it's a contiguous block of memory, right? So it's just like a chunk of memory, if you'd like, and it's divided up into the slots that we talked about. And typically, for our purposes, we would only ever put like a single type in an array. So all the slots would be the same size. So we wouldn't have like an array of integers that's mixed with like an array of strings or something like that. We're just going to keep them all the same type. And so in a language like C++ or C, we have to decide ahead of time how many elements we want to allocate space for when we create an array. We have to kind of state that up front. So let's go through just like creating an array, and this is just an array of 5 integers, okay? So this is the C++ code. I've just got declaration of a 5-element integer array, and then I've got a for loop that's just printing it out. Anybody guess what the values are to start with here? 0?
Yeah, it's
Counter thoughts?
I think I would start with
How about that?
That's not it.
Anybody think about that? Okay.
Never mind.
So, C++, when it gives you a chunk of memory, whatever's in that memory is in that memory. In this case, when I ran this program, this is what was in it. So that's what these elements start off as. So the first thing we're going to do, this could be anything, is we're going to go ahead and set those to 0 when we initialize it. Just so that we have a nice clean slate to work with here. We don't have any surprises. Okay, so let's kind of think about a task where, say we've got this 5-element array, and we're going to be receiving positive integers. To make things easy, we're not going to receive 0. It's going to be 1 or greater. And all we want to do is put them in this array and keep them sorted. Okay, so we want the lowest integer to be at 0 and the highest integer to be at index 4. So we can start, say we get 12. We need to add 12. That's pretty easy. We just stick it in the first slot there. 14, it's also pretty easy. We just put it there in the next slot. 15, doing really well here. And now 1. So what do we have to do when we receive 1 in this case?
Wait.
So it's got to come at the beginning, right? It's the lowest one.
Oh, you like switch spots, like put. You gotta swap.
Right. So obviously, like 1's got to be in 0, right? Well, now 12 can't be there. So if we put 12 in 1, well then 14 can't be 1. So we shift, right? We push them all down the line. Okay. So something to think about, and we'll talk a lot more about this, is how many elements did I have to do something to just to add this 1? So, and so this is small, right? These like 5 elements, right? But when we're working with data structures and they're not just integers and they're in real applications, this can be quite large. So it could be quite expensive to have to move these down this array. Mostly because if you think about what you actually have to do to shift those, is you have to actually copy them over into these slots in kind of a loop. So I'll go ahead and do that. That's fine. Okay, we've got 1 in there now. We've shifted everything. We're good. Add 2.
Now you shift everything again.
Right. So the other thing we have to do, we have to find, where does 2 go? So we do have to go down this array, right? Ours is short, so we only have to look at one element. We say, okay, 1, it's bigger than that. 12, oh, it's less than that. We're in between here.
What is this process called again? I remember it was called. It's a certain like element that's called.
So it's just a naive sort, really. It's like an online sort, like so.
Isn't it called selective store or something else?
I don't think so. The closest, this might be close to an insertion sort, but again, don't hold me to the details of that. I would just call it a naive online sort. And online just meaning you're receiving the data one at a time. You don't have it all in advance. And so you just have to sort it in here as it comes. So to do this, we have to do the same thing. We shift these down a bit, and we put this in the slot where it goes. Okay, so that's all good. Still sorted. Add 4.
But we run out of spots.
Yeah. So we don't have any more space. So what do we do?
Double the size of the array.
Why double?
Because if you just had one, then you want to add another, you have to do that again, and you have to copy it.
Right. Yeah, so that's what we do usually. We double the size of the array, and we keep going. But it's not free to double it. You know, we have to allocate memory, right? We've still got to keep this around while we do that. We've got to copy this over, and we've got to add the new one in. Okay. And that's just how it works with arrays like this. You've got a big block of memory, and you're going to store things in it. If you run out of memory, you're going to have to get a bigger block. And on the flip side of that, imagine that we think like, oh, we're going to need to store, 100,000 elements. So we allocate 100,000, and then we store like 3. We've taken up the space for 100,000, no matter what. That space is not free for anybody else to use. And this is usually okay, but it's not great, and it kind of helps motivate thinking about structures that are not just this linear, sequential, contiguous block of memory. And that's what we want to do. Obviously, arrays are really important, and we need them for things. Specifically when we index, right? An array is great because you can index into it quickly. It costs you pretty much nothing to go to index whatever and pull out the data. So it's a very fast random access. The things that are less good about arrays, and again, I'm just talking about like these C++ arrays, C arrays. I'm not talking about like array list or vectors or anything like that. Is that when we insert or remove at an index, it can require shifting quite a few elements around, which is somewhat expensive. If we have unused space, it's still allocated. And then if we have to resize a lot, if we're bad at predicting, the amount of space that we need, then we're going to spend a lot of our processing time doing this resize operation and allocating more space while we do that. So that brings us to linked lists. And linked list, I kind of want you to think of as just like an entry point to different data structures that are not so reliant on this sequentially accessed table of memory. So in a linked list, we do things just a little bit differently. And what it revolves around is the idea of nodes and links to other nodes. So we can imagine this. If this was our array, this is what it would look like as a linked list. So each element is kind of in its own little container here, and each element has a reference to the element after it. There are good things and bad things about this, but it does help us with some of the things that the array was costing us on. So for example, let's go back to adding 4. If we have our data in a linked list, to add 4, the first thing we're going to do is create a new node. And so we'll go through code in class. We'll build the whole linked list and software in here. And we'll start that on Friday. But essentially, when we think about this, and you can think about it in object-oriented terms, you can think about this little box being its own class, right? And like maybe it's just got 2 fields in it, 2 members, 2 properties. One of them being the data itself, and one of them being, in our case in C++, a pointer to the next node that's next to it. So like, just to maintain like the order that we had in our array, we've got these, and each of the next ones points to the next one. So it's important to note that these pointers are pointing to the bigger box out here. So the next it's It doesn't point to the next, and it doesn't point to the next value. It points to the next node, which contains both. And that'll be important as we implement this in code. So we've got our 4. So the first thing we would do when we get the 4 is we would say, okay, we need a new, and we can just, let's just call it a node class. Okay, so we'll call the object a node. We need a new node, and the value, the data is 4. And in our case, we're just storing integers. You could store any type you wanted. You can do, if you're really fancy, you can do templating. We won't do it by mandate in here, but that's the way to do it if you really want to build a generic system. You can say, I can have a linked list of anything, and like the user or the programmer supplies the type that they want to use. But for our case, let's just pretend we're just doing integers. So we've created our little node. It's got a next pointer that doesn't point at anything at this point. And we've got our value 4. So now what we need to do is find a place to put it in our list. And we're playing by the same rules, so we're trying to keep it sorted, right? For our linked list, we always typically have something called like front or head or start, whatever you want to call it. And that's just the first element in the list, always. So whenever you take your linked list object and you want to start doing something, you want to look at the data in it, you can ask it, can you give me your first node? And then from there, you can follow the chain. So you can see we're trading off the ability to randomly access this, right? We can only come through front and follow this path. So that does mean, if you think about we're searching for something in this, we have to go through it all, right? Until we find it. And the same thing if we want to insert something in here, we have to find the right place to do that. So let's start by finding that place. We'll start at the front. And so we come to the first node, we see it's a 1. That's less than us, so we'll continue on. We move to the next node, we see that's a 2. We need to keep going. Then we see a 12, and that's our stop. Okay, easy, right? We found where we need to put this guy. So to do this, all we have to do is take this pointer that was pointing to 12, the node that holds 12. We remove that. We have 4 here in its node. We'll move it here, and we'll add its next pointer will now point to 12. And then all we have to do, change this guy to point to 4. So now that's connected. What we saved here is we didn't have to, like the array, allocate another chunk of memory, copy everything, shift it, do anything like that, right? We just had to go find that spot. As soon as we found the spot, these are really quick operations, right? We're just saying, oh, now you point here and you point here, we're good, right? So this is kind of the general idea in terms of doing these data structures that are not based on indexing. And we'll explore a lot of different ways you can do this. So this is kind of the most basic, right? We're just point this element to that element to that element, you know, down the chain, right? You can imagine, why just one pointer? Like, why couldn't it point back to the one before it, right? That would be a doubly linked list, so it's pretty popular. It could point, you know, 3 or 4 directions, right? And that's where we start to do things like graphs and trees and other structures. So let's briefly talk about some performance considerations. So we'll think a lot in this class about 2 things, space and time. We want to know how much room we need to do something, and that's in terms of memory. And we want to know how much time, how many operations we have to do to complete it.
So we don't have to use arrays in here anymore?
You don't have to use, I don't think there's any reason you would have to use arrays, but you're going to have to write a linked list, so.
Yeah, arrays was.
Yeah. So some things to think about are what's better comparing this to arrays versus what's worse. So here's a little bit of some intuition on that. If we think about accessing an element based on an index that we know, there's no question arrays win. Indexing is fast. Linked list, we have to go through it all to find it. If we're talking about adding or removing at the beginning of the list, then linked lists win. Linked lists have a reference to their beginning. It's one lookup for that, and then a couple more operations to put a new node there. With an array, you're probably going to have to shift things, and it's possible at some point, always with an array, that you may have to resize. But that's, it's not always the case. That's just in the worst case. If we want to add and remove at the middle, we kind of have an even split here, right? The linked list, we have to get to the middle. So we have to go through all these elements. We have to navigate it. With the array, we have to move things. And then if we want to add and remove at the end, as long as our linked list is built in a certain way where it has a reference to the end, that will be just as fast as it is with an array. So we won't talk about today what this means, but this is big O notation, and it's just a way of talking about the worst case that something takes to perform, so an operation. So this is kind of the equivalent of that for arrays and linked lists for these operations. And you'll see that we say like big O of 1, that means it's pretty much, it's a constant. We know it's only going to take like 3 operations, right? If we need to put something at the beginning of the list, that's just how it works. If you see something like big O of n, that's saying that it's roughly the size of the data structure that we're working with. The number of elements in that is what we consider our worst case to be. And we'll talk a little bit more about how to actually arrive at these values. It's sometimes a little bit involved, but just to give you kind of an initial taste of it, and you could kind of, from your intuition, feel it, right? You know what operation you had to scan through a bunch of stuff to do, or move a bunch of stuff, versus what was, I just had to change the address here and there. So that's all I want to do today. On Friday, we will continue with this, with more linked lists. Please be sure to sign up and do your challenges by Friday.